HGST. He's going to do a talk on SMR. So I don't know how many people know about SMR drives or kind of the current next generation technology that's going to be hitting the shelves very shortly. Raise your hands. Anyone knows about SMR, about Shingle? Ah. Luckily, Manfred's going to go for a real deep dive here for us, as well as doing some bits and pieces on HGST's product line and how that's going to affect us, and then probably have a brief discussion afterwards about especially larger capacity drives and how that's going to fit in with ZFS as we slowly grow the capacities up from 4, 6, 8 in the up to 10 terabytes per drive. So without further ado, here he is.
Okay. Thank you very much. Yeah, my name is Manfred Berger. I hope we have sufficient overlap in the languages we speak. I'm an engineer, not a software guy, so I learned doing punch cards on an IBM 1130 when I did my degree, so nothing to do with the stuff that you do today. And yes, I'm going to do a deep dive, but how deep is deep? So actually, I want to start on the surface and then see how far we get. Here's the environment we work in as a hard drive manufacturer. What's changing landscape for us is the hyperscale in data centers, which is driving new opportunities for one thing. But the go-to-market shifts are changing from the OEM model that we were in for years to an ODM model, which accommodates stuff that you do, because it's basically non-branded hardware running independent software. Cold storage, which is evolving and fragmenting. There's new interest in tape on optical, which is not us, but nonetheless, it does exist. And here's one of the main reasons why I'm talking about SMR. It's the challenge to increase data density on a single platter. So we have to do things in a different fashion. Good growth in SSDs in enterprise. We love that. We sell those as well. There's a gradual transition from 3.5 to 2.5 inch in desktop, which concerns us to a degree. The notebook market is stabilizing at a low volume. And again, there's growth in cloud and hyperscale, which again ask for things like ZFS. The yellow ones are the ones that are really driving SMR as an initiative. When we decided what to do in order to increase capacity, we had a number of building blocks to choose from, HAMR being one, where in order to make the bits smaller and yet thermally stable, we use a magnetically very hard material and soften it temporarily with the use of a laser or microwave. That technology today is a few years away, and so we can't really use that at this point in time. And it also adds cost. The present prototypes last for about 4,000 hours, which is really not enough for a storage device. The benchmark is more like 40,000. We could go to two-dimensional magnetic recording, where we analyze data left and right of the original track in order to reduce the error rate in reading, which then allows us to put tracks closer together. Again, something that's not quite ready. We could go to bit patterned media, where we physically separate the magnetized portion from its neighbors on the hard drive, which again gives us more stable magnetic bits. The challenge is we can't really write them individually, so we actually have to write these in an SMR fashion as well. So SMR is not going away, and that's why I'm making all these points to generate this understanding. It's not a one-time thing, it's here to stay, so you better learn to deal with it. Then another thing that we have done a while back is we introduced helium into the drives to reduce friction, reduce power, reduce vibration, and so on. So that's here to stay. And that makes HAMR work better, because the problem here is heat. Helium is a very nice medium to actually cool, because the molecules are 1/7 the density of air, very mobile, cools them nicely. So it helps HAMR, but it doesn't really break it. I mean, it doesn't give the breakthrough. And then SMR, which is another thing available to us, basically at no cost, just software, and that's free, as you all know. So that's what we decided to go with. So we're left with two things, and the focus is really on helium and SMR going forward for the time being. Both are multi-generation technologies, as I indicated, so BPM works better with SMR, HAMR works better with helium. If you don't have either one, you basically fall a step short in the development. And the other good thing is we understand both technologies very well, so we don't run into any technology or reliability risks if we do that. And this is the total landscape. Since we introduced the hard drive to the market in 1956, we had a 50 million times improvement. We just slowed down a little lately. hoping for these things to eventually become available. So LMR, or longitudinal magnetic recording, is out of steam. We're here with PMR today. SMR is the next thing. And beyond 2017, we think we got HAMR working to a satisfactory degree. But again, with helium, most likely with SMR. The product we're shipping today is the HE8 with 8 terabytes. So that's been in the market for a while at 1.1 gigabits per platter. And introducing SMR gets us to the HA10, or in other words, 1.4 gigabytes per platter. So it's basically a 25% capacity bonus you get by introducing SMR. And that's the first drive that will hit the market. We do utilize helium, as I indicated. We do utilize SMR. Some people call it cold storage because the usage model is slightly different. I'll get to that. But actually, with the right software, you get just as much performance out of SMR that you are used to from a vertical recording. And that's why I brought my notebook. These animations don't usually work on an Apple. Not that I dislike Apple, they're a great customer. So in an air-based device where you have helium and oxygen, which comes in atom pairs or molecules, in other words, you have pretty heavy gas, in other words, which creates friction and vibration on the drive, so it gets very hard to actually follow the tracks. Whereas in helium, it runs much smoother, lighter, and with less power consumption and noise. And it enables a few things. We can make the platters thinner because they don't need to be as stiff as they would have to otherwise, which allows us to put more in the same device. So it increases density in the data center, and if you're paying for space and boxes, you appreciate that. There's less drag, 23%. Even though we did increase the platter count, we still consume 23% less power, which means the device is running cooler, which either allows you to bring the data center up by 4 degrees or allows you to bring it up while the drive still retains its temperature 4 degrees cooler. And it results in higher reliability overall, which isn't relevant for one drive. If you have one drive, it either works or it doesn't. If you have 1 million drives, reliability dictates how often you have to run to the data center to replace broken hardware. We announced helium in 2012, and at that time we had a few years of internal experience, so we decided let's do it. We announced the platform. In 2003, we actually started shipping the first model with 6 terabytes. We meanwhile introduced an 8 terabyte version, and at the same time announced a 6 terabyte drive in air and said this is going to be the last one of those models. Early this year, we had the 1,000th helium drive shipped, and the next 1,000,000 is literally around the corner. But in between, actually this June, we will bring this 10 terabyte drive to market. Helium did help reliability, but originally we didn't put it in the spec because to really test 2.5 million hours MTBF, you have to put in quite a lot of test time, and we decided to ship it at the original specification, which at the time was 2 million hours. Desktops are here. Competitive home office enterprise drives or NAS drives are at 1.4 million hours MTBF. We started from 2, and having been in the market for a while, we now have the data that proves the actual reliability that we achieved so far is 2.5 million hours mean time between failures, which means a group of 1 million drives reports an error every 2.5 hours. And it's not the end of the flagpoles. We know there's more in the technology, but we don't want to test it because that costs time. We just wait for the market feedback and put that into our calculations. And now SMR, finally. Traditionally, when we increase the capacity of a drive, we make the tracks narrower, but we maintain a gap between them. To magnetize a film that is very hard magnetically, we need a stronger field, and that has the disadvantage that it also strays to both sides. So for that reason, we accept that SMR is writing fairly wide, but then we overwrite part of it. So we get benefits both ways. We get smaller, dense, stable bits, and we still get to small tracks by overwriting. But as you can imagine, rewriting somewhere in the middle here is a problem because you would write wide again and kill the previous content. So you have to write sequentially, but not the whole disk. You can actually write in individual zones. And I'm going to talk about that in more detail. So this is as wide as we write. What we're left with are the small bands that we can read comfortably with the sensors we have available today. And this is what the head looks like when you're on the media looking up. This pole actually generates the write field, and we left it open to one side, which gives us a stronger field down to the media and allows us to write data denser. Yeah, I think I covered all these. Now, layout, yeah?
Is it a different pole that does the writing from the reading then?
Yeah. For several generations, we had a separate read element and a separate inductive write element, so we could optimize them individually. One advantage being that we've always been writing wide and reading narrow, so we're used to that. It's just we never overwrote in the past. Yeah. So we had to take a few decisions. One is, how large will we make an SMR zone? It could have been 64 or any number short of infinity. And with the size, you actually decrease the number of zones you have on the drive. On the other hand, between zones, we need gaps because you eventually need a breakpoint at which you can start rewriting again. If the gap is only 2 tracks, we get to that kind of utilization of the available storage area. When we make the gaps wider, we get to it eventually, but only at fairly large zone sizes. And it's very hard to manage something in the order of 262 gigabytes a piece.
So why would you trade off more tracks gap versus less track, like a 2-track gap versus a 64-track gap?
I'll get to it. The narrower the gap, the more influence there is from one active zone to the neighbors. I'll explain it on the next foil. Good question, but one page too early. We basically decided on this operating point here. So we'll have zones that are 256 megabytes in size, a fairly large number of them, with a gap of only 2 tracks. And here's why. If this happens to be a very active write zone, this stray field of the head will eventually influence signal quality on its neighboring zones. The effect is there today. It's called far track interference. It's not new. The hard drive industry is used to deal with it. There's another effect called advanced track interference, which is an influence on the immediate neighboring track. That goes away because we're writing sequentially, so we're going through the zone. But the larger stray field eventually has an impact on the quality. So we can rewrite that. We monitor that, of course, and we can rewrite it. But it takes about 5 seconds should we have to. So in the design, we have to consider what's the use case of the drive and what are the background functions we need to keep the data live, right? Because the benchmark, again, is 40,000 hours. Now, on the host side, you have various options. We can try to make the drive behave in a fully transparent fashion, manage everything on the inside. It has been tried, not by us. It looks okay when the drive is fresh out of the box. Once it has been used for a while, it drops to something like 3 IOs. Once all the buffers are full, all the media caches are full, you're left with something like 3 IOs, so not necessarily good. So we decided drive managed is not something we would go with. There's another one, and that's why I'm talking to you. You can actually make it host managed, where you need special commands. You need to be aware of the zone size. You need to be aware of your write pointers. You have to write sequentially and so on. What you get in return is a very high throughput and a very well prediction of that throughput over time and with block sizes and so on. For that, you have to change to these 2 commands, whether you're on T10, which is the SAS, you would use the zone-based commands, or if you're on T13, which is SATA, you would use the zone ATA commands. You would largely write sequential, but not at a single point. We actually have hardware support to write at 16 different areas of the drive. We can support more by firmware, but then you see a slight overhead increase. So as long as you stick to the 16 write points on a drive, that can be done. there are no additional changes required with that, and the drive behavior is very consistent and predictable. Now, there's another one where the name host aware was picked, which basically is an invitation to write bad code. That's why I'm pointing that out. Because if you tolerate commands as they come in, you'll never have the code fully debugged. There are things that will bring performance penalties. And that's why this is actually much preferred, because it will abort every command with an error if it's out of sequence, if you're trying to read behind the right pointer, if you're writing in a zone without resetting the right pointer to 0. So all these things are very well controlled, and at the end of the process, your code is very clean. And once you wrote the code, you can actually apply it here. So a host-aware drive will tolerate bugs, and therefore there will be bugs by definition. And in the end, you have unpredictable performance once again. So if you do the work, why not do it here, right, and get the good debug done? The industry said, okay, we agree, drive managed, no good for us. Host managed, yes, but do we have to? Should we? It was seen as a temporary thing, but it really isn't, because the gains are permanent. With every new technology you introduce, you're still that extra bit ahead with SMR. So it's not a throwaway software solution. And host aware was perceived as the ultimate, because then you just get away with doing what you did, and no real mandatory changes. Now, over time, the closer SMR came, basically, and the more people actually thought about it, they said, okay, this is still not the way to go. This is emerging as the best options, because at the end of the process, we will have clean code, and then we could switch to that, but why, right? So let's say if we were the only ones having this and you wrote code for this, you could apply the code on others as well. But it's not mandatory, and as a result, throughput is unpredictable. Now the future is that these two, host aware or host managed, will definitely come. One might eventually migrate to that, even though I personally would not prefer that as an engineer. There's another option coming, but it's fully transparent. Should we switch to 2D MIR, you would not notice. It's completely transparent to the host, doesn't come with any new requirements. Now talking about the layout in more details. So we give away about 1% of the drive capacity for a random write zone, because you have to have some place to put your metadata, right? You don't want to write metadata on blocks of 256. And 1% doesn't sound much, but actually it's 100 gigabyte, which I think is plenty. Then you have the sequential write zones with the gaps in between. In the host managed, a write zone will always remain a sequential write zone. If you do a random write into these zones in a host aware drive, it will switch from the sequential mode into random mode, which doesn't actually do anything here. It's just the data will be somewhere else, and you'll have to manage an indirection table internally, which is a bit of a challenge. You want that to be power safe and all these things. And then the conventional zone is this one, is part of the addressable user space, so you have full control over that. The media cache, which you would utilize in the case of a host-aware drive, is not part of the user space. So that's where the data lands when you're writing out of sequence, just to save the situation and keep the data somewhere. The next zone is the sequential write preferred zone for the host-aware implementation, or the one that is definitely sequential write only in the case of the host-managed implementation. Here's what the media cache looks like. We had invented that because of SMR, and then found it quite useful in our PMR drives as well. So what it does, creates zones to drop data into across the whole surface. So wherever the head is, if it's a small write, rather than doing a seek and a wait for latency and then drop the data, we just drop it wherever we are. And on a PMR drive, we get about a 2.5 times random throughput performance, which is good. On SMR, you have to have that if you're not host managed. Right? We don't think you need it with host managed, because you will write in a proper sequence only. And the whole thing is managed by so-called write pointers, and that's the one reason why you need a different command set. Because you could write with a standard command, you could read with a standard command, but you need to know where you are. And for that, you need to manage these pointers on the host side. And should you ever lose them, you need the command to ask the drive here, where am I? Which zone is full? So that's what the new commands are there for. The actual read and write is no different. And then there are a few recommendations, like you should never read beyond the write pointer because nothing is there, at least no valid data. And you should always write at the write pointer and then increment that until the zone is full. And then you get to the next zone, but you should not write across boundaries. You should write to the end, then reset the pointer to 0, which is, we could allow it, right? But again, it's just an invitation for bad code. If we said, well, you haven't set it to 0, so we don't want you to write there. Because you could accidentally overwrite existing data there.
And could you potentially skip some portions of the zone? Because that would make it really possible to implement ZFS on top of it. Or easy.
Yeah, you can, but then there's no data there. I mean, these things are not written. There's no initialization pattern or whatever. So it creates difficulties, but physically, you don't have to.
No, I'm talking about, say, for instance, I've written to the zone previously. I've reset the write pointer back. There's still the same data I've written there, but say, for instance, I just want to overwrite some of the data in a linear fashion and skip some portions that I want to keep.
No, you can't keep, right? Because you're starting at 0, you're writing wide, and even if you stop here, you've already killed some tracks.
I'm fine with losing a few of them.
Yeah, no, that is not recommended. We could imagine appending with a gap, but then the gap is full of garbage, basically, so why do that? And you're not the first to ask. Actually, the drive manufacturer suggested that in the standards committee. So that's the media cache. And now some software aspects. So if we introduced an SMR drive down here, did nothing else, all the applications running on the system could not write to it. They would just flag errors. However, you could perceive writing an application that actually talks straight to the hard drive if you wanted to. You could have the application talk zone-based commands, but it's not really recommended. What we do recommend is you introduce a library that does that sequencing for you, and then the application talks as if it talks to a standard file system, and we do the translation in this layer, and then everything else is the same.
Can you explain that? Are you saying that there is no file system, or you've implemented the file system in libzbc?
Yeah.
Okay, and then that talks directly to the disk without using the file system that's implemented in the kernel?
Yeah, it follows the write rules. There's some flexibility how you apply that, and as I indicated, I know Fortran from 1978.
So what's the advantage of, you're essentially implementing a whole new file system, and you're doing it in a userland library. What's the advantage of doing that versus like implementing that new file system in the kernel, the way it's traditionally been done?
We thought it's easier as an add-on, and I'm getting to some of the details that might explain why we did what we did. Okay. Yeah. So that's what we recommend, to enforce data to be written in sequence. And this is what we make available. So basically the library, an emulator, so that you can take a standard drive and by driver fake it to behave like an SMR drive for your actual debug, and some sample applications. And all that is on the next page, is on GitHub. So that's where you find all the documentation, where you find code that should compile on your machine. And with that, you should be ready to go and give it a try. Now I have to go back one, actually. So this is what we asked for. Launch with host-managed SMR. Do the sequential writes, which is enforcing clean code. You can migrate to host-aware later on. You have to start with a SAS drive because T13 has not released the package. You should consider 256 megabyte fixed zones, which is pretty close to ZFS, which is at 128, I was told. And again, I'm not a software guy here. Other zone sizes are possible, but this is what we're shipping. This is what we're shipping. And we already make full capacity samples available, and the announcement is planned for in about 2 weeks' time. Then it becomes real to hit the market. But if you have detailed questions, please go to GitHub, look at the documentation there, have a go.
So is your vision of the solution that file systems will cease to exist and instead people will use your library, or that people will integrate that functionality that's in your library into their file systems and then the library will not be necessary, or some combination of the above, or what?
Yeah, it's entirely up to you. The thing is just an offer, right? You can put everything in the kernel as you want. It just, I think, gives you a quick start by seeing the applications, by looking at what's in the library, see how things work. You can have access to the source code, and then you're free to do your own thing, basically. So it's our library is not the industry standard. It's just to give you a kickstart.
So you don't really have any recommendation or vision. You're just like, here's some hardware, and here's how you might be able to use it, but maybe you'll integrate with ZFS. Maybe ZFS will just die and people will use it,
right.
Or maybe,
Yeah, exactly.
Okay.
Because combined, I think you'll be much smarter than we just had to do something, right?
Well, if talking about integration, what's the license on the library, just out of curiosity?
Yeah, no, there's no license on this. This is just open source.
Well, open source still frequently has a license. Just want to ask about versus public domain.
Public domain?
As far as I know, yeah. I mean, you don't need to register. You just go there and have a look.
Yeah, but I mean, if it's GPL, then it can't be integrated into other, into Linux.
I suggest you have a look at the agreement there. I didn't read that. We have no intention of licensing anything. We just want to get people like you going at it, and that's why we thought it's a good idea to make some code available. Yeah.
The question on the zone size, is that something that is still in flux, or?
No, this is how we'll ship.
And is that standard across all drive manufacturers, or?
As of this point, yeah. There was one customer asking for less, but we would have to give up like 4% capacity. But for now, and the battery just died on me here.
What's 128 meg? It's not 128K.
It's pretty big, yeah. Yeah. Sorry, David, you're next, but the battery's dead.
I also have a question about the zone side. Does a write need to be exactly 256?
No. You can append single blocks if you want.
So you can append within a zone.
Yes.
So I start with 100 and then another 100.
Yeah, absolutely.
So that's no problem.
You have to be sequential within the zone.
Sequential
you
within
can
zone,
append, yes, any size, 512 or greater.
Okay.
And you can have multiple zones open for write. Right? You don't have to squeeze everything in the same.
So you could actually have multiple zones with the right pointer somewhere within it, and as long as, but you don't have to finish writing to that zone. You can skip to a different zone.
Exactly.
As long as you continue sequentially writing to the end before you repeat, you can switch between any zone and just request where the right pointer is, and then start writing.
And the number is not limited, so the firmware will handle any number, but eventually get to a very big table with a big overhead, and we only manage 16 in hardware at this point. So no penalty there other than performance. And actually, it's not just the battery; it's the whole notebook froze. maybe the application lost.
So
focus.
you should have brought an Apple.
Yeah. Okay. No, it was box. This box message changed the focus. Yeah.
I just have a very basic question, like on the overview of this. Now you're talking 10 terabytes, which seems just a little bit above the normal hard drives that are currently available. So the reason to deal with all of this new way to deal with things and complexity and difficulty is because this type of technology is going to go a lot higher in capacity per drive than the normal drives, or is it going to be like now, which is a little ahead, but it's not.
Today the gain is 25%, and we expect this gap to get to about 50%.
So it's like we deal with normal hard drives, and we're like at 10 terabytes, and if we want to go to 15 terabytes per drive, then we have to go with this
SMR.
technology.
And the promise there is you get that at the same cost, right? Because it's
But same cost per terabyte or same cost
same
total?
cost per device or lower terabyte
So
cost.
a 15 terabyte SMR, you call it? SMR drive will cost the same as a 10 terabyte normal drive?
Yes.
Okay.
Yeah.
And I have another question, but this time it's for the ZFS creators. Is that compatible with ZFS? Is that feasible? Is that to have like a zpool add strange drive something, and then have ZFS be able
Somebody
to
has to do a lot
store
of work.
data on this
Like,
drive?
This is like thousands of hours of work.
It's not trivial.
So it can be done
make this
tomorrow, right?
compatible. Yes, tomorrow does have thousands of hours in it, doesn't it?
Okay, so it's extremely difficult to imagine that ZFS could actually deal
There's some concepts that
with
overlap,
that.
which is nice.
It's not in there at this point. It's feasible. Well, a lot of things are feasible, but is it worth it? If people are willing to pay for it, I suppose so.
And that kind of goes to a question I had for you. You mentioned that Hammer and Helium would kind of be the technology that you guys would pair together. Where do you see a lot of the investment in doing SMR today if Hammer may not necessarily be SMR? Is it going to be shingled in its technology when it comes out?
Today we don't see Hammer without shingling because we can get the laser spot to the right size, but the magnetic pole just don't get any narrower. The smallest we have created is 60 nanometers, and we would have to get to something like 10 to really have a big impact there. So we don't see it today. That's why I said initially SMR is here to stay. So it applies to all the technologies I showed. And yes, so it's 1,000 hours, but then it's this 50% bonus on every future hard drive, right?
Any more questions? I suppose look, I do have a question, which is, with SMR going forward, we see it because, I think it's something as ZFS we might have to deal with just because, what's the projective lifestyle on a PMR and that roadmap going forward. So it's, there's obviously going to be some limitations, and then that's going to slowly decline in manufacturing numbers, and then that always has an impact on availability and then the investment going forward.
If you remember the curve, it's actually already in the pretty flat part, and eventually the engineering effort,
down.
because engineering brings you forward in time, but if it doesn't bring you up, it's not worth the investment, right? So even though there might be a few percentage gains still.
So looking forward to the hackathon project tomorrow then. So